Okay, so welcome to our first Boundary Layer live session. So everybody is default muted, and as people come in, they should come in default muted, and you will not be able to unmute yourself until Brian finishes and is prepared for questions. I'll go ahead and do the introduction today and for the rest of these just to keep it more simple for everybody. Once questions are open, I'll allow you to unmute yourself, so go ahead and unmute yourself and please do ask questions. We'll do our best not to talk on top of each other, but we're all learning to do this as we go, so just try to be respectful to each other. When you are not speaking, please do mute yourself. That way you don't stomp on somebody else's question. And if you have the internet bandwidth and feel comfortable doing so, consider having your video on. I'm going to leave my video on, so you might see some kitties come over. This is more to support Brian than anything else. It's kind of awkward to deliver a speech to no one, so some nodding faces and some pets might help. So we can go ahead and get started then. My phone number is in the chat window, if you can pull up the chat. If for some reason something's going wrong and you're not able to, I don't know, wave at me or whatever on the screen, please do feel free to send me a text message. I have my phone right here. Today's speaker is Brian Green. He's a fourth-year graduate student here at OU, and he earned his master's degree in meteorology here in 2018. Brian is originally from the suburbs of Chicago, but graduated from the University of Illinois in 2016 with a BS in physics and atmospheric sciences. Since moving to Narman, Brian's been able to work with Phil Chilson in the Center for Autonomous Sensing and Sampling to develop drones for sampling the atmospheric boundary layer. His research has taken him on field projects and conferences across the globe, namely Spain, Finland, Japan, and now his home office. Today, he'll be talking about his research on characterizing turbulence in the Arctic stable boundary layer using data collected during the 2018 ISOBAR campaign, using a novel combination of in situ drone observations and recent advances in SBL theory. So with that, I'll go ahead and let Brian take it away.
Great. Thank you, Liz, for that introduction. Thank you all for taking time out of your home office life to come and witness this glory in Zoom conference networking. I think this is, I'm really thankful that OU has this technology capable for us to be able to try to smooth out some of the bumps in all of this craziness that's going on in our lives. So in that spirit, I want to try to keep this kind of lighthearted today, you know, some casual turbulence theory and whatnot. So I do have a couple of alternate seminar titles for you guys today, including Understanding the Atmosphere in Remote Locations That You Can't Catch COVID-19 Way Up in the Arctic North. My dog gives me bad coding advice, and I'm pretty sure my wife is sick of me at this point, and it's only been about a week and a half. All right, so why do we care about turbulence in the Arctic boundary layer? Well, a lot of global models have grid spacing that's on the order of several kilometers, and a lot of the momentum, moisture, and heat transfer throughout the boundary layer occurs on scales way smaller than that, on the order of meters and even smaller. So they require a lot of different types of parameterizations in order to kind of make up and guess what this momentum transfer might look like in real life. And what a lot of these are based on goes way back to the 50s from Monin and Obukhov with their similarity theory that scaled velocity, temperature, and stability in terms of atmospheric surface layer based fluxes. And those are given here for the equations as a refresher. Basically, a characteristic velocity is related to the amount of turbulent mixing U prime W prime bar. And this has been used for decades, kind of without question by a lot of communities because it's really hard to do a lot better. There have been other advances in other types of extended Monin-Obukhov or non-local scaling. But really what it comes down to with some of these difficulties, especially in the stable boundary layer, is that Monin-Obukhov similarity theory is very susceptible to self-correlation in that both the input parameters and the functions that yield your new profiles have the same parameters in them. So you're kind of making something out of nothing. People have shown that you can get really good looking relationships with purely random noise, but that's not good. Especially in the stable boundary layer, this definition of stability, Z over L star, is also a ratio of fluxes. So that's our tau naught over H naught. That's our momentum flux over our heat flux. And when you have really stable conditions, you have really intermittent and possibly non-existent turbulence at all. So both of these kind of tend towards zero. And you get this problem of a 0 divided by 0 condition, and it looks basically the same as near neutral conditions as well. So this is a pretty poorly defined parameter in order to understand turbulence in a wide regime of the natural world. A lot of models kind of get around this by tuning turbulent diffusion and prescribing different types of ways to get around this throughout the day. Some recent advances based on the SHIBA research campaign back in the late 90s, early 2000s, is by characterizing turbulence using scales based upon local gradients in basically temperature or potential temperature. This is earliest in the literature, goes back to around 2010 from Sorbian. He's kind of been the leader in analyzing a lot of this SHIBA data. That was a field project, basically a year worth of data. They had a ton of instruments sitting on an ice floe in the Arctic Ocean, basically continuous data for nearly a year. And they got some incredible results from that. But they also showed that if you scale the turbulence using these three sets of parameters, so that's Z is altitude, gamma is our local stability, and beta is the buoyancy parameter. G is gravity, and T naught is just a reference temperature at the surface. So you can then scale your velocity, temperature, and length using much more or much lower order moments in the atmosphere. And then if you also scale that based on local Richardson number, the turbulent parameters collapse to a really nice even function of Richardson number with different regimes for different stability regimes. So what's cool about this is that when you can create these universal functions of Richardson number based on local fluxes, you can then back out turbulent parameters and your fluxes by evaluating only measurements of your local wind and temperature gradients. So I think you might see where this is going next. If we take ourselves to Finland, up in the Great White North, about 65 degrees north, we participated in a field campaign in February 2018. This was the Innovative Strategies for Observations in the Arctic Atmospheric Boundary Layer. I believe I talked about this last year in my seminar, so this should be not too much news to most of y'all. But for those of you who aren't as familiar with your Northern European geography, here is a map of Scandinavia. If we zoom in on Finland, is this country on the right. We were on this island off the coast here called Helijohto, and it was off the westernmost coast edge of the island. This looks like a tropical paradise, but in reality, it was more of a winter hellscape. I mean, frozen winter wonderland. Here is an aerial image using satellite imagery and overlaid with GIS, the different instruments we had going on during the campaign. This blue area is where we had fixed wing airplanes or fixed wing UAS were able to fly large swaths with turbulent measurements on them explicitly. But we were more focused on this little red domain here where we would fly profiles with UAVs, rotary wing UAVs. And then you can also see the location of a couple surface towers and surface-based remote sensors. And I'll go over those briefly here as well. So we had our main tower was a 10-meter mast with 3 different levels of eddy covariance. Okay, Cece is sighing at me. She's already tired of me talking. Eddy covariance at 3 levels, temperature and humidity also at 3 levels, and then we could also get radiation balances and ground heat flux measurements. We also had 2 different SODARs, a 3D scanning wind profiler, as well as a vertically pointing one, and then a WinCube V1 LiDAR wind profiler that was operating for the majority of the 2018 campaign. That gave us pretty good resolution in 3D wind fields. But the big gem of this campaign is it was really the first instance of incorporating drones into measuring the boundary layer for this big of an endeavor. There were really 2 different categories of drones we were working with. This was rotary wing and fixed wing. Here are a couple examples of the ones we were using. And the rotary wing were really good for ascending very slowly throughout the very stable boundary layer overnight. And we would profile from about the surface to 300 meters continually throughout the night. And then about every hour or so, the longer endurance fixed wing aircraft would profile all the way up to 1,800 meters, which was the ceiling we were allowed to fly to in Finland. So with all this in mind, this is kind of a workflow for how the rest of the talk is going to go. We're going to look at how this theory in turbulence scaling applies to the data we collected in the towers from the Isobar campaign. We're going to see how well that works with trying to create the reverse problem of applying the new universal functions onto profiles measured by the drones, seeing if that's even physically possible, and then seeing what kind of turbulent parameters back out. And then after it's all said and done, try to start compositing different regimes of different boundary layer flows and see if we can understand some of the more conceptual diagrams of these different regimes. So let's go ahead and get started with characterizing the turbulence from the tower. This is based on 10-minute observations of 10-minute averaged fluxes. The Sorbian procedure used 1-hour fluxes, but we actually showed pretty good convergence of our flux measurements with 10-minute averages. A big key to this is that we had to filter for only onshore flow, because this still, at the end of the day, does require homogeneous and all those fun assumptions of the parameters. So we really only have homogeneous flow if the fetch is across open sea ice and water. Calculated gradients analytically by fitting second-order polynomials to natural log of altitude of the data. And after it was all said and done, this kept about 10% of the observations, which doesn't sound like a lot, but for continuous 10-minute profiles, we still had several hundred to thousands of data points that went into these averages. So here I'd like to show the scaling of the momentum flux versus Richardson number. We can see the different colors represent the different altitudes of the different observations. So we had eddy covariance measurements at 2 meters, 5 meters, and 10 meters. And in general, aside from the 2 meter being a little bit lower than the line, this is probably related to ground effects, and the Richardson number also being kind of poorly defined at much higher stabilities. A lot of these collapse to a really nicely defined function. This is defined as our momentum flux divided by our US squared, and that is based on, again, our vertical gradients in momentum. Sorry, that would be, the US was from earlier. Okay, so for temperature, we also see probably better fit to the empirical line. This black line is the empirical one developed in the older papers, Sorbian 2010, Sorbian and Grachev 2010. And we can see that we still have a pretty similar function for when we look at our heat fluxes, normalized by U and T, respectively. So that took a very long time of processing to get to that point, which is really exciting that it still showed up to be pretty appropriate scaling when the stably stratified flow has fetch over ice and sea. So we'll keep that in the back of our minds moving forwards. Now we can get into analysis of some of the drone data. So we want to be able to apply this to vertical profiles measured from the UAVs, but estimating vertical profiles of Richardson number is not necessarily an easy task, because when you have measurements coming in, our post-process data were at 4 Hertz, and all the minute little tiny zigzags in all of your parameters kind of make calculating vertical gradients kind of blow up. And you get really unphysical results for all these different things. So we also have to deal with the fact that comparing quasi-instantaneous profiles to 10-minute average data also presents an inherent problem in this analysis. So the way I've been approaching this is by kind of downsampling and smoothing and getting general fits of the different profiles, as opposed to all the fine scale, minute, small details, all the little zigzags. So I downscaled to 0.5 hertz, which gave a DZ of about 2 meters. I did a low pass filter with the Butterworth filter. That was semi-arbitrary after looking at the spectral analysis of the temperature and wind speed measurements from the different drones. And then again, gradients were calculated iteratively by fitting second order polynomials and calculating the gradients analytically. So a quick example of what this might look like in practicality is here's a profile from one of the Copterson flights from one of the evenings. 21 UTC, 2146 UTC is well after sunset. You can see the black lines represent the raw profile, and you can see how crazy that looks in wind speed. And the dashed blue line represents what the filtered and downsampled data look like afterwards. So this is a much smoother profile in all these different cases, and they give much more reasonable, here's Richardson number on the left, much more reasonable characteristic values of Richardson number. And if we compare that to just backscatter from the vertically pointing SODAR for the same time period, we can see a similar regime of internal boundary layers occurring just from the backscattered versus the different peaks in Richardson number versus height as well. So we haven't really dug into some of these case studies yet, but this is really good physical validation that this procedure might be on to the right train of thought. So really what I'm getting at is that these physical profiles can be attainable after processing in low pass filtering, downsampling, really careful attention to detail with all the different profiles. We can get pretty reasonable looking measurements of vertical gradients. So moving forward into applying the universal functions, I didn't put in the empirical functions that Sorbyan and Grachev came up with, but they are pretty gross. But basically, you just have to reverse them, and you can plug in a value of Richardson number and your local scales, and then it will output vertical or measurements of momentum flux and heat flux shown here. I've color coded based on whether the flow is offshore or onshore, just for some internal validation. And then the blue dot is what was measured at the same time by the 10-meter sonic at Ecovariance Station. So from this profile, this is the same one that I showed earlier from Richardson number. We can see some pretty reasonable looking results. They're at least on the same order of magnitude as the tower measurements. We can see a couple spikes at different levels in both momentum and heat flux. Analysis and physical understanding of these is kind of beyond the scope of this study, but I would love to chat with people about some of these interpretations of some of these profiles. But what I was trying to get out of this is, even though we do have offshore flow, we're still in the same, school of thought. We're in the right ballpark. There we go. We can also estimate velocity variance, vertical velocity variance, and temperature variance from these relationships as well. I've also overlaid the LiDAR vertical velocity variances. I don't know how appropriate these comparisons are because I don't know if this incorporates beam broadening or aerosol scattering or any of that. But at the very least, it shows a somewhat similar, it has this little nose here at, I cut off the altitude, I think that's 100 meters, as does the copter profile. And again, we're in the same ballpark with measurements from the sonic anemometers. So there are probably about 100 different profiles throughout the campaign that I have post-processed at least. And instead of showing all of those one by one and trying to get an understanding conceptually that way, I thought it would be a better idea to composite some of these profiles based on some type of sorting parameter. And something that I've learned recently is that this is a really active area of research right now in Arctic meteorology, is these multiple different regimes of net long wave surface radiation balance. So it turns out only recently did we discover that in the Arctic, there are still mixed phase clouds even in the wintertime. And that creates this kind of bimodal distribution in surface net long wave radiation. And why that's really important is because it was, when it's really cold in the Arctic, people assumed that all the clouds were entirely ice. But when they discovered that the low-level lapse rates from the Shiba data were nearly dry adiabatic at low levels, and they looked at the surface radiation balance, they were discovering that there was definitely some diabatic heating occurring from the low-level clouds. And that led to a big discovery that these clouds are in fact mixed phase. So in our case, we do see a pretty similar, this is a PDF of our surface net long wave radiation from the 10-meter tower. And I chose 25 watts per meter squared, or negative 25 watts per meter squared, as a cutoff for where you kind of have these two sort of different regimes going on. Close to zero is when it was cloudy, and below there is when it was more clear. And we do, from just a sanity check mindset, we did see many nights during the ESOBAR campaign where there were low-level clouds, there was intermittent fog. We were looking at the data as they were coming in, and we're like, why are we measuring dry adiabatic lapse rates when we're in the Arctic? And it turns out it kind of all traces back to this. So going forward, I'm building composite profiles of everything we measured based on sorted by our surface net radiation, long wave radiation. Okay, so there's a lot going on in this figure here. It is just our vertical profiles of potential temperature on the left and wind speed on the right. In red is when long wave radiation is greater than negative 25 watts per meter squared, so our cloudy conditions. Blue represents our clear sky conditions, okay? And on the wind speed, the dashed lines are the LIDAR wind profiles as well. And the low, weird, chopped off ones at the bottom represent the 3 levels of the 10-meter tower eddy covariance station. So I want to look first at the blue lines. We can see that there's a pretty strong inversion in the lowest 50 meters. If you look at the tower data, all the profiles should have been normalized to the tower, but because the tower was continuous throughout the entire month period and we only had so many profiles, there's going to be a natural offset. But what I'm really more interested in is the vertical slope of this. So if you kind of just slide that to the left in your brain, the low-level gradients actually match up really well with what the tower with what the copter is observing. Good morning. Hi, Cece. So we see a really strong low-level inversion basically throughout the entire depth of the atmosphere, kind of neutraling out around 200 meters in blue. And we see a stronger gradient in wind speed as well in the lowest levels during the clear sky conditions. And then to counter that, during the cloudier sky conditions, we see a basically almost entirely neutral stratification profile going up to all the way up to 150 meters and then increasing from there. And that matches actually really well with the conceptual model for how Arctic air masses are formed, in that the low level cools and you get cloud formation and then you get an inversion on top of that. So the top of that inversion is kind of roughly where the top of the cloud base might be in general. The wind profile, I'm sorry, I didn't mention the shading on all of these are the interquartile range in all of the different profiles. So 25 to 75 percentiles. And the lines are the medians of all the different profiles at each level. And we can see that the wind speeds in general are a little bit slower in the cloudier cases, and you can kind of see where the top of that profile at 150 meters, you do see kind of an inflection point in the wind speeds as well, which is pretty interesting. And although the LiDAR, again, was continuous through most of the campaign, not as concerned about the magnitude of the variables, but the slope of them matches surprisingly well for both the red and blue cases here in general. So if we go ahead and apply our Richardson number calculations and smoothing on all of this to get vertical profiles of Richardson number from these composite profiles, it kind of turns into a mess. Richardson number greater than 0.25 classically is the limit for turbulence to exist, but it has been shown that Richardson number can exist up to low single digits. So there's clearly some problems going on in these lower levels where it's spiking up past 20, 40, etc. But the different levels here, this is still pretty hot off the press, figuring out how to smooth these out and make some physical sense of these. Because I definitely think there's a lot of physical meaning behind these composite profiles of the individual parameters. But when it comes to the Richardson number, I'm just not quite as sure how to interpret these results as of yet. And then, so let's go ahead and blindly apply our backing out the turbulent parameters through all of these based on the Richardson numbers. Again, red and blue are characterized the same way. Blue is the clear sky, red is the cloudy sky. We see some interesting features of turbulent mixing around the 150 to 200 meter mark in that region where we saw that inversion starting to begin. But these are all to be taken with pretty big grains of salt. These magnitudes are are very, very small if you don't look at these types of things very often. So what can we really take away from all of this? I think there's a lot to be learned so far with this type of study. First of all, it's very encouraging that the gradient-based scaling at least holds for the tower-based data. That definitely could use some more cleaning up, which I've been meaning to do as well. But the fact that that still holds is entirely useful and creates the precedent to be able to use the drone data, because the type of drones we're using, like the Copterson that I'm sure you all are really familiar with, we're not explicitly measuring turbulent parameters on that. We're using just thermistors and capacitive hygrometers to measure temperature and humidity. But if we can find a way to estimate turbulence by just measuring temperature and humidity profiles, that can be such an enormously useful framework to understand the boundary layer. And the way we kind of got around comparing apples to oranges between 10-minute fluxes and drone data is kind of just attacking head on this question of the classical framework of Reynolds average turbulence. What does that even mean? Low passing all the data. And I think a really interesting avenue that I've talked about with Scott Zaleski a bunch is the concept of uniform momentum zones. I won't really get into that here, but that's a really cool topic I'd love to talk about if y'all have any experience looking at an engineering literature on that. I have been meaning to combine, because the Copterson wind speeds are so, you saw how noisy those profiles were. When the winds are so weak, it's so largely affected by its own propeller wash. Trying to back out some profiles based on the remote sensing wind profiles could be a really good avenue to pursue. I've tried that a little bit and it turned out not great because of the resolution. And then moving forward with some actual hard science studies is this regimes of clear versus cloudy profiles of our traditional thermodynamic parameters really show some distinct features. And moving forward, I'm looking to categorize these between onshore, offshore flow, because that's a pretty important caveat to a lot of this turbulent framework. So I don't really know where we are on time. I think we're still doing pretty good. So with that, that's all I've got for today. Thank you all for sticking by. I hope the captions were keeping up pretty well, and I hope the audio is coming through nice and clear. So thank you all so much.
Thank you, Brian. As far as from my side, it looked like it worked out pretty well. And I believe I've given everybody permission to unmute themselves. I can see all of your faces, so if you're trying to unmute yourself and you can't, just wave around. Does anybody have any questions for Brian at this time? Go for it.
So with the processing of the LiDAR data, did you account for the noise and the line of sight velocities, or did you do any of the Lin-Chao processing or any of that kind of stuff to try to get rid of that noise?
So what I'm working with is already processed NetCDF files. I don't know what went into his side of processing, because I know he has available 1 second wind speed profile data. I don't know how good those are, but I have no idea what went into his vertical.
I assume he was doing the multiplexing method to do that.
I assume so. I've been meaning to catch up with him more on that. He's pretty swamped. So the guy who made all of these was supposed to submit his dissertation last week. I have no idea what his timeline is right now. But yeah.
Yeah, I could just see it being a lot of the line of sight velocity uncertainty is contaminating and biasing both those vertical velocity measurements as well as the just regular old 1 second wind speed.
Yeah, for sure. And especially when we're in such, I mean, at least in the clear air masses, that's pretty pristine air masses up in the Arctic. So I don't even know what kind of aerosol backscattering opportunity there is. So
yeah, that's the other thought I had as well.
Cool.
Brian, you said the noisiness and the wind direction data was because of the low wind speeds?
Yes. Let me go back to that. Here.
Yeah, it's been a little while since I dove deep into wind data from the copters, but do you get the same noisiness when there's high wind speeds, or does it tend to be more smooth?
I think the higher wind speeds helps to smooth that out, and just the fact that we're using such a simplified model of, this goes back to Tyler's seminar 2 weeks ago. We're calculating wind speeds and directions in the same manner that he did, or that he talked about in the beginning of his talk. So not correcting for ascent or anything, but I do see less noisiness, just as I guess it's a variation of plus or minus half a meter per second when it's 15 meters per second versus 2 meters per second makes a big difference.
Brian, I had a question about the mixed phase regimes you brought up. Yes. So the Shiba data, that you mentioned that was prevalent in that data set too. And those data, from what I understand, were used to develop some of these empirical functions, some of which you actually evaluated here. I haven't spent a whole lot of time myself looking at how that was done, but what does that impact of these mixed phase regimes, what is that on these empirical functions? Is it separated for these regimes? Do we understand enough about these regimes in the stable limit to develop separated functions?
That's an awesome question. And I haven't seen anything personally that separates them or that combines these two. I think I have, is it still showing my screen here? Whoop, come on. I actually have the paper up right now that I was thinking of. And most of these papers don't really talk about the turbulence so much as just combining low-level stability and temperatures and whatnot. So I don't know if the science is there yet. I would love to dive down that road, though. This is, for those interested, is Python et al. 2014, Climate Dynamics.
Are there any other questions for Brian?
Hey, Brian, I had a question.
Yeah.
So as I understand it, you were using these empirical functions to back out some of the fluxes from the copter profiles, correct?
Right.
So with those functions, is there kind of a built-in critical Richardson number that doesn't give you any flux after a certain stability? And does that match with the turbulence that you're seeing from the data?
So that's a great question. They have they have identified in this gray shaded region, Richardson number beyond on the order of 1 is when things start to break down for them. And I think our data show a similar response around Richardson number 1. They kind of level off at neutral stability. So Richardson number going to 0. But that is, yeah.
Yeah, I mean, I think as you mentioned, that's kind of a big question, right? Like, when do you have turbulence past this critical Richardson number? Sometimes you do, sometimes you don't. It's not really like this firm upper limit. So yeah, that's very interesting.
Yeah, and we just didn't have a whole lot of observations with that strong of stability as well, interesting enough.
Mm-hmm. Thanks.
Mm-hmm.
All right, last call for questions.
Cool.
Well, if not, I think we can go ahead and thank Brian with our invisible claps, or silent claps, I guess they're not invisible. And thanks for being the guinea pig on testing this out, Brian.
Yeah, thank you, Liz, so much for facilitating.